All right, so we are going to be applying our understanding by justifying behaviors of functions. So it says, following is the graph of two functions defined on the interval AI. One function is g of x, whose graph is the solid curve. So that is this curve that is solid. The other function, h of x, is the graph that is dashed. One of these functions is the derivative of the other. So our goal is to find out if h prime of x is the derivative of g, or if g prime of x is the derivative of h. So we're going to decide which of these alternatives is correct and support our answer by describing the intervals of increase and decrease, by describing the horizontal tangents, etc. Okay, so looking at these two graphs, I am looking for highs and lows. So I would look at g of x, for example, to start, and I would say, okay, it is decreasing from A to almost C. So if it's decreasing from A to C, then its derivative should be negative. And if I look at h, I'm like, okay, well, h is negative. So maybe h is the derivative of g. Let's look at the alternative. H of x is increasing all the way to about e. So if a graph is increasing, its derivative needs to be positive. Is g of x positive from here to there? No. So I can determine from that very beginning of the graph that h of x is the derivative of g of x. So we're going to say that h of x is equal to the derivative of g of x. And I can assert that by looking at those key features I just discussed. So the thing is, you might be able to look at the graph and make that assertion. But in calculus, you need to be able to describe all of that in words. So we're going to go through each of the key parts and we're going to describe in words what's happening to tell us that that is true. So not just why that is true, but what on the graph indicates that truth. So I'm going to use the blank space. You can label your graph as we go along. I have a picture of the graph over on the side, so that's how I'm giving you the information. But the first thing I want to talk about is the horizontal tangents. So where does y of g of x, so where does g of x have horizontal tangents? So g of x has a horizontal tangents at x equals c, because it is a minimum on that graph. I would say at x equals h for sure, and at x equals f. I know all of those answers because I can look again at that graph. So I'm going to erase that and go back up to my graph. And I know that g of x has those horizontal tangents because h of x has zeros at c, f, and h. So if the derivative has a zero, then it is a critical point and there is a horizontal tangent. Remember, critical points do not imply extrema. Critical points do not imply extrema. So let's do this. Let's shrink our graph a little bit so that you can see what I'm writing as we're discussing. Let's talk about the point x equals c. So let's talk about this particular point here. So at x equals c, h of x goes from negative to positive. If the derivative goes from negative to positive, then at x equals c, what? If h of x goes from negative to positive, then x equals c is a local. In this case, negative to positive tells me decrease to increase. So we can say a local min of g of x. So you'd say at x equals c, since h of x goes from negative to positive, it is a local min of g of x. That is the written justification for the local min of g of x. I can't say g of x has a local min based off the graph. You have to tell me why g of x has a local min based off of its derivative graph or actual data. That's what the first derivative test says. So we could say something similar. We could say at x equals h, because h of x goes from positive to negative, this is a, and you could say relative instead of local, max of g of x. So in order to be a max of the function, you have to describe the positive or negative behavior change of the derivative. And for that reason, we know that f is neither a max or a min because there is no sign change. So at x equals f, because h of x does not change signs, g of x does not have an extrema at that point. So you might get asked, where is there a time that the derivative is 0, but an extrema does not exist? That answer would be at f. And then we could also talk about intervals of increase and decrease. So where is g of x increasing? G of x is increasing when h of x is positive. So where's the dashed line positive? From C to H. Now, 0 is not a value of positive or negative. So AP accepts the interval C to H. If you're in a college class or you're considering engineering, they're looking for the understanding that you can identify that F is not positive. F is 0, and 0 is not positive or negative. So technically, g of x is increasing from C to F and F to I. Or if you're in AP Physics, Mr. Mannon would not accept F as part of his answer because F is a point of rest. It's a point at which that object is not moving. It doesn't change direction though. So it's just one of those weird little points to consider. And then where is it decreasing? Well, it's decreasing when h of x is negative. So that would be from A to C and H to I. Oops, sorry. This one should have been H, not I. So that was F to H over on the left. Sorry. Okay, so lots of key pieces of information from two tiny little graphs. We have increasing and decreasing, we have extrema, we have non-extrema, we have horizontal tangents. And then, like I said, yesterday we introduced concavity. So let's look down at one more part. So part 2 says, suppose f of x equals x cubed over 3 minus x squared over 2 minus 2x. Where is f of x increasing? Where is it decreasing? Explain your answer. So again, everything on AP, and you can tell this handout was from AP College Board. So I try to really use those AP handouts because that's what they're expecting. These are worded the way AP would word a problem. So this wording is AP worthy. They're looking for an explanation. We know that you as students can do math. I know you can find the derivative of this function. I'm not concerned with can you find the derivative. I know you can find the derivative. So f prime of x is x squared minus x minus 2. I know you can do that. What I don't know is can you determine what that derivative represents? So what do the zeros of the derivative represent? Well, when the derivative is 0, we have these things called critical points. And those critical points represent potential change in direction or change from increase to decrease. So we have these critical points where the function is 0. And what we want to do is determine what's happening around that function at those critical points. So what's happening to the left of -1? What's happening between -1 and 2? What's happening beyond 2? So at 0, and that's just the easiest, 0 minus 2, it's negative. Bigger than 2 would be 3. So 3 minus 2 is 1, so that's positive. 3 plus 1 is 4. Positive, positive, positive becomes positive. Plug in -2. -2 minus 2 is -4. -2 plus 1 is -1. Negative times a negative is also a positive. So what this tells me is this is a sign chart of the derivative. So my original is increasing from negative infinity to -1, decreasing from -1 to 2, and increasing from 2 to infinity. Sorry. Okay. What connections do you know between the derivative of a function and the original function? Suppose you are given a graphical representation of a derivative. So we're given the graph. All right, I'm picturing a derivative graph in my head. How can I use this graph to determine what the original function is increasing or decreasing? Well, just like the example above, if the derivative is negative or below the horizontal axis, you want to talk in terms of graphing words. If the derivative is negative or below the horizontal axis, then the original function is decreasing. And then conversely, and I'm just out of room because we're writing on the iPad, if the derivative is positive or above the horizontal axis, then the original function is increasing. And then suppose you're given an analytical representation of a function. So now we're given a formula. How can I use the formula to determine where the function is increasing or decreasing? So in order to use a formula, you have to find the critical points of the derivative. And then find where the derivative is positive and negative. So you have to find the critical points of that and then find where the derivative is positive or negative. So we're looking for sign changes between the two. Those would represent the extrema. Okay, so hopefully that helps with your understanding of the beginning of 4.3. Like I said, we're going to continue today to look at concavity and the second derivative test, and just kind of continue to create the connections between the original, the derivative, and the second derivative. So we have a particle, and particle motion was actually one of your areas of issue on that recent AP classroom activity. Both questions that were most commonly missed had to do with particle motion. So I want to make sure we really continue to focus on particle motion because it's not going away. So a particle is moving along the x-axis where the position function is given by x of t. Time for a particle moving along the x-axis must be greater than or equal to 0 because time cannot have a negative value. Find the velocity and acceleration and describe the motion of the particle. So again, this goes back to the handout we did where we did particle motion and we made our sign charts. So we did that back in about December. So those sign charts and particle motion are all coming back into play. And now we're just talking about the graphical part of play. So what I want you to do is find velocity. So we'll do velocity in red. So our velocity is 6t squared minus 28t plus 22. Our acceleration is the derivative of velocity, so 12t minus 28. And then to describe the particle's motion, we need to find the zeros of velocity and acceleration. So I can factor out a 2 of my velocity equation. And then I'm going to factor So since I have a positive and a negative, I know both of my factors are negative. So I have 2 critical points on velocity. The time when it is 1/3 and at t equals 1. So these are the points at which the velocity is at rest, or the particle is at rest and the velocity is 0. So these are potential changes in direction. Potential changes in direction. These are my critical points. Acceleration can also have PPOIs, potential points of inflection, at the zeros. They also give the times when the acceleration is changing, so we can look at speeding up and slowing down. And that would be at 7/3. So now we're going to look at sign charts. Remember, we can't go beyond 0. Okay. Sorry, 11/3. Oh man, missed my one. Okay. So find your values between 0 and 1, 1 and 11/3, and 11/3 and beyond. And then you also have to find the signs of acceleration between 0 and 7/3 and 7/3 and beyond. So if you plug in 0.5, 0.5 minus 1 is negative 0.5. 3 times 0.5 is going to be 1.5, but 1.5 minus 11 is also negative. So you have positive, negative, negative. So 2 negatives make a positive. So you have a positive between 0 and 1. Between 1 and 11/3, and 11/3 is like 3.6. So you could pick the number 2. So if you plug in 2, 2 minus 1 is 1. 3 times 2 is 6. 6 minus 11 is negative. So positive, negative, positive gives a negative. And like I said, 11/3 is kind of like 3.6. So you could plug in 4, you could plug in 5, anything you want. Heck, you could plug in 10. So you'd have 2. If you plugged in 5, you'd have 15 minus 11, so that's positive. 5 minus 1, that's positive. So positive, positive, positive makes a positive. So when it says describe the motion of the particle, it is moving right from 0 to 1, and from 11/3 to infinity, it's moving left from 1 to 11/3. For acceleration, we would plug in, so 7/3 is roughly 2 1/3 or 2.3. So we would plug in a number like 1. So 12 times 1 is 12. 12 minus 28 is negative. Plug in a number greater, so maybe 4. 12 times 4 is 48. 48 minus 28 is positive. So we're not talking about concavity anymore. We're talking about acceleration. So the acceleration is decreasing from 0 to 7/3. And it's increasing from 7/3 and beyond. But again, we don't talk a lot about acceleration. We talk about speed, and we talk about speeding up and slowing down. So a particle is speeding up when the signs are the same, and it is slowing down when the signs are opposite. So from 0 to 1, velocity is positive and acceleration would be negative. So the signs are opposite. Therefore, it is slowing down from 0 to 1. From 1 to 7/3, they would both be negative. Therefore, it would be speeding up. From 7/3 to 11/3, velocity would be negative. And from 7/3 to 11/3, acceleration would be positive. So they would be opposites. So it would be slowing down. And then from 11/3 and beyond, both would be positive. So therefore, we would be speeding up from 11/3 to infinity. So we talked about the second derivative test yesterday. The second derivative test finds the points of inflection or areas of concavity for the original function. Well, the second derivative test can also give me key pieces of information about the first derivative. So we can also use the second derivative test to test for extrema without actually even needing the first derivative. So there are multiple ways that we can use all of our derivatives to help me understand what is happening. So one way is to look at the zeros of the derivative. If f prime of c is equal to 0, so if the derivative is 0, that tells me that the original function has a horizontal tangent. I can look at the sign of the second derivative to determine if that 0 represents a max or a min. So if the sign of the second derivative is negative and the sign of the original, or the sign of the derivative is 0, then the original has a local max. If the derivative is 0 and the second derivative is positive, then we have a local min. What that would do is eliminate the need to make a sign chart for f prime. What that would do would eliminate the need to make a sign chart of f prime. The problem with this alternative second derivative test is if the second derivative is 0 or does not exist at point C. So there's only this one teeny tiny minuscule case in which this alternative second derivative test would not work. So we can do it and apply both methods in example 2. So it says using the second derivative test to test for local extrema. So what we're going to do is find f prime we have to find the critical points of f prime. So now I need to know if this value on the second derivative is positive or negative. So I'll find my second derivative. And then I want to find f double prime of negative 2 and f double prime of positive 2. So I get that the second derivative at negative 2 is negative. So the second derivative at negative 2 is negative. So that tells me, according to my chart, if the second derivative is negative, then x equals negative 2 is a local max. So to write that out as a justification, we would say x equals negative 2 is a local max of f because f prime of x equals 0 and f double prime of x is less than 0. We can look at 2 and say x equals 2 is a local min of f because f prime of x is equal to 0 and f double prime of x is greater than 0. And if you want to confirm that, you could make your sign chart of f prime. Put negative 2, positive 2. Plug in numbers above and below each of your critical points. So again, 0 is always the easiest. It's negative. Plug in something like 3. 3 squared is 9. 9 times 3 is 27. 27 minus 12 is positive. Plug in a negative. Well, negative number squared is positive, so that's also positive. And we can see that the original is increasing, then decreasing, then increasing,
confirming that -2 is a local max and +2 is a local min. So again, what's in blue is the alternative derivative test for extrema of the original. So I know a lot of you this whole time have probably been thinking, okay, well, I could just graph the originals and find all of these points of concern. I could just figure out the increasing and decreasing and the max and mins by looking at those graphs. Obviously, it's not going to stay that simple, or it's not going to be that easy. They may not give you the original function. So in example 3, I don't have f of x. And yeah, okay, in physics, you kind of know how to find the antiderivative, but you don't know the initial conditions, so you can't find the constant of integration, so you still can't find your answers without initial conditions. So you have no choice but to apply the first and second derivative test to find these areas of increase and decrease. So if I'm given the derivative and I want to find the increasing and decreasing of the original, I need to find the critical points of the derivative. So the critical points of my derivative are 0 and 3. Now, when you factored out 4x squared, how many x's did I remove? In this case, I removed 2. So that means that this answer of x equals 0 is what we call a repeated root. X equals 0 has what we call a multiplicity of 2, which means that that answer occurs twice. Because this is a cubic function, that tells me I need to have 3 roots or solutions, and I do because 0 is repeated. So that's just something important you need to keep in mind when you're getting your critical points. And you're going to see why that repeated root is important in our test. So again, we have 2 ways we could go about doing this. We're going to do it both ways just to practice. So you have the sign chart method, which is the first derivative test. And then we can also use the second derivative test. So for the sign chart, we have every key piece of information we need. We're going to make our number line. Now remember, the number line means nothing on the AP exam, so you have to put it into words. So I have f prime. I'm going to look at the numbers below, between, and above. So that's -1. Well, a negative number squared is positive, so that's positive on the outside. -1 and -3 is a -4. So a negative times a positive is a negative. Plug in 1. 4 times 1 is positive. 1 minus 3 is a negative. Positive times a negative is a negative. And plug in 4. 4 squared is 16. 16 times 4 is positive. 4 minus 3 is positive. So that is positive. So that 0 is like that blip on our graph. It's like the H graph where it hit F, but it didn't cross F. So this graph is going to be double decreasing from negative infinity to 0 and 0 to 3. So our original is kind of like decreasing, and then I'm going to do it in black. So it's decreasing, it has that blip, and then it's decreasing some more, and then it's increasing. So 3 would be a local min. So in order to really understand increase and decrease with that second derivative test, you have to understand how you get a max or a min. So the second derivative test would say, okay, here's f double prime of x. What's happening at 0? What's happening at 3? So 3 squared is 9. 9 times 12 is 108. And then 9 times 24 is like in the 170s. So 128 minus 170 makes this number a negative. And again, I don't really care what the number is. I just need to know its sign. So if the first one's 0 and the second one is, I just had that wrong. 3 squared is 9, 9 times 12 is 108. No, it's negative. Yeah. That 0 here, if you go back, and it won't let me go back on my slides without erasing out of my writing, so I was trying to think of what I wanted to do. That 0 creates an issue where that second derivative test fails. So remember I said there are only certain cases where the second derivative test does not work. And when you get that 0, that tells me my second derivative test fails. So that's why it's so important to recall, remember, and know how to apply our first derivative test. Negative, negative. So again, this is like the case I talked about earlier with you, where when you have a 0 that is a non-negative or positive, you have to take into account that technically my graph isn't increasing or decreasing at that 0. So we have it's increasing from 3 to infinity and decreasing negative infinity to 0 and 0 to 3. So we already found our second derivative. We're going to bring and transition that over to this slide. And we have a GCF of 12x. So we can take that out. And then find our PPOIs, so because it says identify any points of inflection. So your PPOI are the points of inflection in which the derivatives are equal to 0.
So we have 0 equals 12x and 0 equals x minus 2. So we have x equals 0 and x equals 2. So we're going to do our second derivative number line test. If I plug in a negative, 12 times negative 1 is negative. Negative 1 minus 2 is negative. Negative times a negative is a positive. If the second derivative is positive, then my graph is concave up. Plugging in a 1, 12 times 1 is positive. 1 minus 2 is negative. So that makes this negative, which means my graph is concave down. Plug in 3, 12 times 3 is positive. 3 minus 2 is positive. Positive, positive is positive, which means my graph is concave up. So, concave down, concave up. If you have a change from concave down to concave up, or you change from positive to negative, then you have a point of inflection. So these are no longer possible points of inflection, they are actual points of inflection. So I have a point of inflection at 0 and a point of inflection at 2. It's concave up from negative infinity to 0 and 2 to infinity. It's concave down from 0 to 2. And now that I have all of those key pieces of information, I can sketch a graph of this function. So I know a couple things. I know that I have a repeated root. I know that I have a local min. I know where it's decreasing, I know where it's increasing, and I know where it has concavity points of inflection changes. So I got to take all of that into account when I get my graph. Your graph and my graph should be similar, but they can also be different. So the horizontal plane in which we draw it on could be shifted up or down. What cannot change is the locations of the extrema and the locations of the points of inflection. So I know at x equals 0, my graph has a repeated root on its derivative. So what that means is on my original, my graph is going to be decreasing in such a way that until we get to 3, because 3 is my actual minimum, this graph is consistently decreasing, but it has this blip right here at 0 where I have a change or a little bit of a min, and I have a change in concavity. Then at 3, it makes a big turn and goes back up to increasing. Actually, that's kind of. And at 2 and 0, I have points of inflection. So you can see at 0, it went from concave up to concave down, and then it goes back around 2, and I could even maybe do it, oops, change it a little more. so that it's a little more precisely at 2. I hate that on Zoom it erases my whole graph. So you can kind of see that point of inflection is occurring at 2. Again, your graph could be shifted up, it could be shifted down, it could be a little bit closer. So maybe your blip is down there, and then you have this. So the graphs have like these little bit of points of change, but not much. Without graphing, sketch the curve x squared over x plus 8. So we focused a ton back in the day on domain and range. So the very first thing I'm going to do is identify my domain. So this graph has a domain of all reals for the numerator, but the denominator has a vertical asymptote when x equals -8. So my domain is all reals except x does not equal -8. And then another easy thing to always find are my x and y intercepts. So the x-intercept occurs when y equals 0. So 0 equals x squared over x plus 8. So you multiply both sides by x plus 8, so that zeroes out. And then we get x equals 0. So what's nice in this case about the x-intercept and the y-intercept is they are both 0, 0. So I'm guaranteed on my graph the point 0, 0. Then we like to talk about vertical asymptotes and even odd or neither. So if you go back, we have f of -x getting plugged in. So I can't factor out a negative. It's not simplified back to the original. So this is not even or odd. It is neither. Vertical asymptotes come from denominator equaling 0. So I have a vertical asymptote at -8. And this graph, because the numerator is greater than the denominator, my horizontal asymptote is a slant. So I have a slant asymptote, and I don't need you to find it, just know that it is there. Then we're going to find, actually I can just stay on that page since I had to erase, our derivative. So that's ho d high minus high d ho all over ho ho. And our critical points come from when the derivative equals 0 or does not exist. So the zeros come from the numerator, and the does not exist come from the denominator. And in this case, we already know the denominator does not exist at -8, and our zeros of the numerator are 0 and -16. So doing a quick sign chart. This time we're a little bit more negative than we're used to. Plugging in something less than -16, and again, it's easiest to look at the top kind of factored out. So I would kind of pull out an x, leave myself with x plus 16. And then I know in this case, I don't really care about the bottom because the bottom is always positive. Because if you square anything, it's always positive. So we're only really looking at the signs of the top. So you have a negative on the outside, a -16 plus 16. Oops, sorry. If you plug in 17, you got to go less than it. So negative on the outside, -17 plus 16 is negative. So negative times a negative is positive. Bottom's always positive. So this is positive. Plugging in like -10, you have -10, which is negative, -10 plus 16, which is positive. So you have a negative over a positive, which is a negative. Plugging in -1, because it's the closest to 0 without being 0, you have a negative, you have a positive, so you get a negative. And plugging in 1 or 2, you have positive, 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 positive. So that tells me that my original function is increasing, decreasing, decreasing, increasing. So that -8, we already know, is a vertical asymptote. So that means it's approaching a negative infinity and coming from a positive infinity. Finding my second derivative. You have ho d high minus high d ho all over ho ho. And then what's nice is I noticed this has an x plus 8, this has an x plus 8, and here's an x plus 8. So that's going to become cubed. That's going to go away, and this one's gone completely. So I have x plus 8, 2x plus 16, minus 2x squared plus 16, all over x plus 8 cubed. So I need to find my zeros of top and bottom. So again, I don't have to simplify this to find the zeros. I know it does not exist in the denominator, which is going to once again be that -8. And my numerator, I can just set equal to 0 and simplify. So I can FOIL all of that out. So you have 2x squared. I'm going to actually go on the next page or clear this page. I have 2x squared plus 16x plus 16x plus 128 minus 2x squared minus 32x. So minus 32 plus 16, 2x squared minus x squared, I'm left with 128. So the numerator is always 128. Therefore, f prime double prime of x never equals 0 because it's always positive. So on my number line, I only have my -8, which is that DNE. So I'm going to compare the values to the left and to the right. This time, the denominator is x plus 8 cubed. Therefore, the bottom can be positive or negative. So the top's positive, the bottom can change. So if it's -10 plus 8, you get a negative number cubed, so that's negative. If you plug in a bigger number like 0, it's positive. So concave down, concave up. This is not considered a point of inflection, even though you have a sign change, because it's not in our domain.
Yeah. It can't equal 0 because you get your zeros from the numerator, but the numerator doesn't have a variable. So there are no double primes of the numerator.
You're welcome.
So sketching this, easiest point, vertical asymptote at -8. We know I have a point at 0, 0. And then from there, you're just going to apply kind of like what we discovered. We discovered it was concave down over to the left of that vertical asymptote. We also discovered that it is going to have a max at -16. I'm going to make sure I have a -16 on there. And my max is going to be like, maybe we say it's down here. And since I know it's a vertical asymptote, I know it's approaching that infinity. So it's concave down, has a max at -16, and it's down there like that. My graph is then, since this is a vertical asymptote, going to start up at the top of that vertical tangent. And then it's going to come down. It's concave up from -8 on. It's decreasing till 0, and then it goes back up to increasing. So it's going to come down, go through that point, and go back up. And that is a rough sketch for this graph. It's obviously not perfect. We're missing, kind of some of those key points. We're missing some features we just don't know. There's a slant asymptote in there. So more than likely, there's this asymptote in here. And, kind of where we have that smooth concavity, it might go a little bit more rough edged like this. It might look a little more like that, but that's not something we're looking in depthly at. So for homework, you're doing that concave up, concave down worksheet, and then